chapter 1 is going to start our discussion of linear equations. In particular, in 1.1, we're just going to talk about equations in general. So an equation has a solution, and a solution of an equation is defined to be a value of x that produces a true statement. Okay? So what it means is if I could take the value that I think is my solution and I evaluate it into my equation, it makes both sides equal. So this question asks, is -2 a solution? So it's not asking you to find what the solution is, it's just asking you to test if this one works. That's actually easier than finding a solution. So you put the -2 in for the x, and you're sort of checking, is this actually going to equal -1? So the negative in the denominator is same as having a negative in front. So this is -1/2 minus 1/2. So what is -1/2 minus 1/2? It's -1, right? They're both negative, so they combine with addition. I keep the sign as negative. So these two are equal. And the answer is then yes. Yes, it's a solution because it actually made both sides equal. If, at the end, you got two values that weren't equal on either side, then it would not be a solution, right? So thinking about that, where we're given a potential solution, what we're going to do next is actually generate the solutions ourselves. And we're going to be working with some equations that just have whole numbers, like the first one here, number 2. Some that maybe have fractions, and I'll show a couple different ways you can work with fractions, and you can take your pick about which one sort of resonates best with you. And then we're going to move into a little bit different of a deal to think about with these equations. So on the first one, number 2 here, order of operations says I should start inside the parentheses, and I understand that, but there's no simplification inside these parentheses that can be done, right? The x, the -5, I can't combine them in any way. So the next order of operations is the multiplication, which we see as the distribution of the -3 across this equal sign, or across this parentheses, So my first step here is multiplication, where I have -3x plus 15 equals 4 minus 2x. When I'm working with solving equations, I want all of the variables on one side, like linear equations like this one. I want all the variables on one side, and I want all the numbers that are just constants on the other side. So you can do that in one step if you wish. You can do it in 2 steps if it helps you to keep track of it a little bit better. I'm going to show 2 steps on this one, just to make sure everybody keeps track of all the values. It doesn't matter which side things move to. I usually move things so that my x value ends up being a positive when I'm done. It's just my natural inclination. Some people always want to move it so that the x is on the left. That's fine too. It doesn't make any difference. But what I see when I do this, and what I'm most inclined to do, is to add the 3x, so that when I add the -2x and the positive 3x, I have x, or 1x. All the other pieces stay, namely the 15 and the 4, and this is a positive x. And then the 4 and the x are joined with addition, right? It's positive 4. So in order to undo the addition, I will subtract my 4. And 15 minus 4 would be 11. Now, if you wanted to, this is one option, right? This is me showing it to you in 2 steps. You could actually do this at the same time up here. If you can manage those pieces simultaneously, that's totally fine. You will still end up getting x is equal to 11 at the end. How could you check, besides looking in the back of the book, to make sure that 11 is the correct answer? Yeah, just like the last problem. You could take the 11 and you could plug it back in, substitute it back in for x into this equation right here at the very beginning, and it should make both sides equal. Okay, so on number 3, there's fractions. And if nothing else, teaching has shown me, it's taught me lots of things, let's be real, but students generally don't care for fractions very much, especially not at an algebra level. You tend to appreciate them more in upper division classes because they're actually easier to work with than decimals, oddly enough. But at an algebra level kind of class, people don't generally like fractions. So One option when you're dealing with a problem like this is to get common denominators, right, and to work through it with common denominators, and that's totally fine. Another option is to eliminate all the fractions to begin with. And that's usually what I do, is eliminate fractions. The way that we eliminate fractions is by finding a common denominator, and a least common denominator is maybe a little bit more helpful, just because it keeps things smaller. So as you take a look at the factors in the denominator, you've got a 2, we've got a 5, I've got a 6, and I've got a 3. 6 is the only one of them that's not prime, right? Everything else can't divide down any further, but the 6 is a 2 times 3. So your least common denominator is found by taking all the pieces of the denominators that are already there. There's a 2, right? There's a 5. I don't need to list the 2 that's there again because I already listed a 2. And there's a 3, and I only need to list it once because it's only inside of each of the values at most once. So if I multiply 2 times 5 times 3, what will I get? 30. 30 is considered our least common denominator. So you probably would approach this from that perspective, or at least potentially so, if you wanted to find common denominators. But you can also use that 30 to eliminate fractions. So here's how that works. What we're really going to do is we're really going to multiply our equation by 30. The entire equation, both sides. You have to be careful because it means you multiply every single term by 30. I want to write it out because I don't want us to lose any pieces of it, at least the first time I'm showing you this. So we can take 30 times x over 2 plus 30 times x over 5. I can take my 30 times my x over 6, and I can take my 30 times my negative 1/3. Okay, so I'm multiplying 30 by each of the 4 pieces individually that I have. The reason I wanted to show it that way is because the 30 is going to make every single denominator disappear. So if I take a look at this 30, the first one, and the 2, I can actually do the division. What is 30 divided by 2? It's 15. There's no more denominator. You could also think of it as simply, what do 30 and 2 have in common? Well, they both have a 2 in common. So divide them both by 2.
Okay, where did 15 come from?
30 divided by 2. Yeah, so you can either think of this, as what I'm doing right here, as that I'm simply dividing each piece by 2, so it's 15 and it's 1. That's what they have in common. Or you can restructure to think that each of these is actually divided by the number that's in their denominator. Okay, so we're going to do all of the last, well, there's 4 more. So if I have 30 divided by 5, I will get 6. Or you could say each of them divided by 5 gives me a 6 and a 1 if you prefer like that. 30 divided by 6 will give me 5. And 30 divided by 3 will give me 10. And there's no more denominators. So what do I have? Well, let's just check it out. I have 15x plus 6x equals 5x, and it's actually minus 10 because there's a negative right here to keep a track of. That's a lot more friendly than the fractional equation that I started with, at least. I can combine the pieces pretty nicely. I have 15x and 6x, which gives me a 21x equals 5x minus 10. What would I do next? I'd move my 5x, so I subtract the 5x from both sides. 21 minus 5? 16x. And it equals negative 10. Then what? Divide by 16. 10 and 16 are both even, right? So they can reduce. Divide each by 2, I get 5 and 8. So x is equal to negative 5 over 8. Yes, Tiffany?
If we can see right away the 5 and 15, can we subtract it?
Sure. Yeah, I think what you're saying is if you noticed right here,
Yeah.
let me actually do it in a different color, but if you noticed right here that you could subtract the 5x, could you do it first instead of combining 15 and 6? Yeah, absolutely. Doesn't matter the order at all. And the reason it doesn't matter is because addition is commutative and adding a negative is addition. So, yeah. The other option, sort of natural option here, is to get a common denominator for the 2 and the 5, which would be a 10, and a common denominator for the 6 and the 3, which would be a 6. Combine them into single fractions, and then to cross multiply. And you can do that. You're just going to be hanging around with your fractions for a little longer if you do that. There's nothing wrong with it, but it is another option. Okay? So there's 3 different classifications for equations that we're going to take a look at. The first type of classification is something called an identity. An identity is something that is true for all real numbers in the domain. In other words, both sides are actually exactly the same thing. Right, so you do a little bit of manipulation and all of a sudden you realize, hey, look, it says 5x plus 3 over the left-hand side and it says 5x plus 3 on the right-hand side. That's an identity. 5x plus 3 means that any x value is going to make it true if it's the same on both sides. Conditional equations is what we see most of the time. Conditional equations are satisfied by one or more real number or numbers, but not by all real numbers. Okay, the last 2 examples that we did were conditional equations. There is one value that worked. In fact, the first example where they gave us the solution for us to test is also a conditional equation. It's only satisfied by one value. When we're dealing with linear equations, generally it's one value. When you have quadratic equations, maybe you have 2 values. It depends on the type of equation we're working with as to if it's one or the more part. And then an inconsistent equation, those have, it has no solutions. So as we're looking at classifying equations, we're going to be doing the same thing that we did on the previous problems. We're just going to be answering a different question. Instead of answering the question of what's the answer, right, what does x equal, we're going to be answering the question of which type of equation it is. But we actually go through the process to find what x equals to do that. So it's almost like what we did already with this sort of additional layer of the last piece added on, identify what kind of an equation you have. So we have 3 of them are listed here. It's a very good chance, and I haven't actually looked at my notes to verify, it's a very good chance I have one of each. That's kind of what I usually do. We'll just see what each of them looks like. So we're going to solve them much like we did before. So on the left-hand side, the 2a plus 3a gives me 5a equals 6a. They're not the same on both sides, right? I mean, 5a equals 6a is definitely not the exact same value. It's not 5a equals 5a, it's 5a equals 6a. So we're going to move them from one side to the other. On the left, I get 0, and on the right, I get a. And I found out that there's exactly one solution, and it's a equals 0. Right? So, what kind of an equation is this? It's conditional. It's the kind we see come up most often. And that's your work to support how you know it's conditional. Okay, so on number 5, what would we do first? We'll distribute. So if I distribute the 4 through here, I get 4y minus 4. And the right side, as already says, 4y minus 4. You do not have to keep going here. Why not? They're exactly the same on both sides. So at whatever point you notice, they're exactly the same on both sides. And maybe you don't notice it right here. Maybe you keep going for another step or something before you recognize, and you're like, whoa, whoa, whoa. This is the same thing on both sides. At whatever point you recognize it's the same thing on both sides, you can stop because you've answered the question it's asking, which is this is the identity. are identically equal. Number 6. Much like the first one, I have 2a and 3a. Now I have 2x and 3x, so I have 5x equals 5x plus 1. So you might be able to stop right here and recognize this is not going to work. But you might need one more step before you do. Because if you're trying to combine the x's on the same side, and you subtract 5x, what will end up happening to this equation? Yeah, it'll say 0 equals 1, and that better sound not right. Yeah? 0 does not equal 1. Right? This is not true. What that means is there's no solution to the equation, and it means that you have an inconsistent equation. Now, why do I say that you might be able to stop one step before if you didn't recognize it? Well, because the 5x is matched, right? So if you have two things that match and you increase one of them by 1, there's no way they're going to match any longer. It's not going to happen anymore. So you might recognize it a step before, and if you did, that would be fine to stop a step before. Again, at whatever point you recognize these are not going to work, you're going to have to do something for me to show that, but what point you recognize it, that's the point when you can stop and you can tell me that it's inconsistent or an identity. Okay, so we started with linear equations, and we're going to take a look at a couple more types of equations today in general. The next one is going to be absolute value equations. Have we talked about absolute values in this class? Yes? Okay. I thought we had, but I've got 3 classes going on with similar overlapping content in different areas, and so sometimes I get a little confused. Absolute value equations. Couple of key ideas. We always want to isolate the absolute value. That's one feature. And the second thing is we should check to make sure our solutions work. Okay, we don't have to check to make sure linear solutions work. We can. It's helpful. That's great. But we don't have to. With absolute value equations, it's a good idea. Right? Because sometimes weird things happen and you come up with a solution that doesn't actually work. And it's usually because you sort of missed something along the way that should have red flagged you and it didn't. And that's okay. But if you check your solution, you'll know. So taking a look at this one on number 7, it's an interesting one. It says I'm supposed to isolate my absolute value. So what would it mean that I would need to do first if I'm trying to isolate the absolute value? Yeah, I need to move my 6. That's what it would look like to isolate the absolute value. Much like isolating x itself, I end up getting that x plus 9 is equal to negative 6. This is a red flag place. You should recognize at this place that this isn't going to work. Because since we've talked about absolute values before, we've also talked about the fact that after you take an absolute value of something, it always becomes positive, right? It's measuring a distance. So I can't take an absolute value and get a negative number. It's not possible. So this actually becomes no solution. Now, if you continue, because you don't recognize this red flag at this point, which sometimes will happen, and it's okay, what will end up happening as you work through the process as though it were a positive 6 instead of negative 6 is you'll end up getting a couple of solutions. But if you check the solutions, they won't work. Right? That's what would happen. So at this point, we get no solution because the absolute value can't equal negative 6. So we're going to do the same kind of thing on number 8. We're trying to isolate the absolute value. So I want the absolute value, the 4x plus 3, and the absolute value to be by itself. So I start what's furthest away from it, which would be my 6, and I move the 6. How will I move my 6 to the other side? What operation? Subtraction it is, you bet. So we're going to subtract 6 from both sides. So what I'm left with is the negative 4, don't forget the negative, and the x plus 3 in the absolute values. And then negative 2 minus 6 is negative 8. Okay, still working on isolating absolute values. So what would I do next? Okay, so do we add or do we subtract? Do we multiply or do we divide? We're going to divide. So the reason we're going to divide is because this negative 4, while it is negative, is actually being multiplied by what's next. So we're going to divide by my -4 as opposed to like adding it. So that leaves me with x plus 3 in that absolute value. And then the -8 divided by -4 is +2. Since it's +2, my problem will continue, right? It will continue on, whereas like on number 7, when I got to this point, I stopped. Okay, so here's something that's different about absolute values than about linear equations that we've done before. Those absolute values mean something. They do. They mean something. They mean whatever's inside could be 2, right? Because if whatever's inside, right, block this out, if this thing that my hand is covering is a 2, the absolute value of 2 is 2, right? So one option is that the x plus 3 is equal to 2. That's one option. The other option is that what's inside the absolute value could be a -2. Because if it were -2 and we took its absolute value, we would also get 2. So we have two possibilities. My x plus 3 could equal 2, or it could equal -2, and it would still solve that equation.
Do you do the addition before you take the absolute value, or does everything become possible before you do the addition?
You mean the addition of the plus 3?
Yeah, so like if the x was -2, for example, -2 plus 3 would be possible.
So I'm not wanting my x to be -2. I want the entire expression x plus 3 to be -2.
Right.
The whole thing.
So that's what I'm asking is, does everything become positive in absolute value
No.
before you do any function?
No, it doesn't. So you're asking me if this instead had said something like x minus 3 inside, would I deal with the negative there?
Yeah, so like,
Yeah.
do you make everything positive inside absolute value before or after you do the function?
You do it you worry about the positives parts at the very end. So at this point, we're actually thinking about what happens inside the absolute value. Everything that's inside here, whatever it is, whether it's positives or negatives, and there might be some negative values inside, right? There might be like a -3 here. We're going to take whatever it is that's inside, and then we're going to set that equal to the 2 and to the -2 to solve. Okay, no matter what it is, no matter whether it looks positive or negative right now, it doesn't matter. It's going to take the exact expression as it's written, set equal to the 2 and the -2.
So like if it said x minus 3, it would be x minus 3 equals 2.
Yes, it would. So if this said x minus 3, this would now say x minus 3 equals 2 and x minus 3 equals -2. Yeah, and I didn't think to say that because that's actually something that I see quite frequently when people make mistakes on it, is thinking that I need to make everything positive first. So great question, Noah. At this point, we can solve these very easily and in the same way, right? I mean, they're both going to be subtracting 3 to get x alone, but I get different values, of course, when I do that. So in the first one, I have 2 minus 3, which is -1. And on the second one, I get -2 minus 3, which is -5. So just let's pause for a moment here to recognize that those actually satisfy the equation we ended up with at the end. That's not actually where I checked generally, but I just want you to see it. So if x is equal to -1, what's -1 plus 3? 2. And what's the absolute value 2? 2. The other one is x equal -5. If -5 plus 3? -2. And the absolute value of -2? 2. So these are the right solutions for this resulting equation down here. That's the absolute value of x plus 3 equals to 2. We would like to go back and make sure it actually works in here. So I know, because I already checked this piece, that this piece right here, this absolute value of x plus 3 is equal to 2. I mean, I checked it here. If I do 4 times 2, what do I get? 8, right? So now what's 6 minus 8? -2, which is what I wanted it to be over there. So these are the correct solutions. We've double checked just to make sure. And we have 2 options at the end. Oftentimes, we have 2 options at the end of an absolute value equation. Not always, you don't have to, but oftentimes we do.
And if you plug both of them in and one of them doesn't work, you just not put in that one.
No, if one of them doesn't work, it means you've actually got an error in your work, is what it really means. Because the answers you get at the end should always work. Otherwise, you've made a mistake. That's not quite true for the rational ones that we're about to start with. There's another sort of thing that can happen, a caveat, but there's nothing that can make this not work except that you've got an error. So if you test them at the end and they don't work, you need to go back and look at your work and make sure you don't have any mistakes made. Tiffany?
If it's a separate operation, do if it's something as simple as x plus 3.
So what I think you're asking, Tiffany, is if I look at the x plus 3 absolute value equal to 2, and I can sort of by trial and error see immediately what the values are, am I okay to do that? I think that's probably fine with me.
Okay.
You could do that at that point, yes. But you're right, they don't always just look like x plus 3. Sometimes they might be more complicated inside, and you might have to show a little bit to get the next point. Yeah. Okay. Okay, one more type of equation today. Rational equations. So we did linear, we did absolute value. Now we're doing rational. Rational means fractions, right? So we're talking about things that have fractions in them. I mentioned this as an option before. We have the ability to eliminate fractions. We did it with an example that had just numbers in the denominator, 5, 2, and 6, if you'll remember that, and 3. So rational equations have a couple different options. One option is that you can multiply through by the least common denominator. Y'all know that that's my favorite option because I like to get rid of the fractions if I can. The other option is to combine each side into a single fraction and then to cross multiply. I'm not really sure that one's necessarily any quicker than the other, but the fractions stay in fractional form longer if you don't eliminate them immediately. So it's kind of a trade-off a little bit. But there is sort of this natural inclination that we all kind of like to cross multiply too. So it's your choice. I think I'll show you what happens if you don't eliminate them on this one first, just because I haven't shown you one like that. And then we'll go the other route on the last example. So taking a look at this, we have 4 over x minus 1. Oh, and it says to always check your solutions. This is actually really important here. It is possible, kind of to answer Noah's question, but for this particular function, it is possible here to get values that absolutely just don't work and you did everything right. In particular, if that were to happen here, it would be denominator value issues, right? If I got x is equal to 1 as a solution, that's not okay. Because if I had 1 as my solution, I'd make the denominator, the first one, equal to 0. If I got x is equal to negative 1 as my solution, I might have done everything right, and it still is not really a solution to the problem. It actually came about because of the way that I solved the problem, and I have to have not include that particular one. So those are possibilities when we have rational ones. When you're taking a look at rational functions, which we've done some rational expression stuff back in Chapter P, anytime you have the ability to factor a denominator, it's in your best interest to do so because you might find that some of your pieces of denominators duplicate. In particular, x squared minus 1 factors, and you know what it factors into because we've come across this a couple of times now. How will x squared minus 1 factor? Yeah, x plus 1 and x minus 1. Agreed? Yeah, x plus 1 and x minus 1. So I don't need to use all 3 of these to try to get denominators that will be all alike because part of each of the first 2 is included in the third one. So if I'm going to deal with this and leave the fractions involved and not actually eliminate them to get at the get-go, I need to multiply the first fraction by x plus 1 over x plus 1, and the second one by x minus 1 over x minus 1. So my first numerator is 4x plus 4. And I don't want to distribute the denominator out. I just want to leave it as x plus 1, x minus 1 in whatever order you wish. And then my second one is the subtraction sign, and then I have 9x minus 9. Now, there is something that's actually kind of nice here. Even though I've kept the fractions for a little longer than I would have in the other step, at this point, all my fractions are actually the same across the entire equation. That doesn't always happen. Sometimes they match on the left, but they don't match with what's already on the right. So if you recognize that that's the case, that's actually really helpful because what it means is that those denominators can now be ignored. Because all I really need now is to consider what happens in the numerator because my denominators are already equal. So I can ignore those denominators. I'm not canceling them in this approach, but I am ignoring them. And then I have that negative multiplying through by the actually, I'm just going to do it while we have this step because I don't want to have to keep writing. Whoops. This one negative multiplies through. So I have negative 9x plus 9. And on the right, I have 3. So we'll combine like terms on the left. 4x and negative 9x gives me negative 5x. Then I have 4 and 9 to give me 13 equals 3. What would I do next? Subtract my 13. So now I have negative 5x equals what? Negative 10. And divide by negative 5. So the x is going to equal 2. Now, while it's a good idea in general, just like on the previous problems, to check and make sure that 2 works, what you're really wanting to check and make sure is that 2 doesn't make denominators equal to 0, because that's a legit possibility inside of rational functions. And it doesn't, right? The 2 is not a problem. X equals 2 is going to work as long as we didn't make any algebra errors now. Feel confident that we're good, so I'm not going to go through to check it. But you can always check problems, especially if you don't have like the back of the book on an odd problem, to make sure that you did it right. Okay, any questions on that one? Okay, so let's take a look at the last example. It's quite similar to the one we just did. What would I do first? Okay, do you know how to factor, Levi? Good. Right. Good. So either as you're piecing it out with trial and error, or as you might recognize it as a difference of squares, this is x plus 2 and x minus 2, which very nicely is the other two pieces, right? So this time, because I didn't do it last time, what I'm actually going to do is I'm going to take that expression and I'm going to multiply it by each of my equations. So x plus, or not equations, but my terms, my rational terms. So x plus 2 times x minus 2, I'm going to do it 3 times because there's 3 different fractions. So I'm actually multiplying the fraction. I'm not multiplying tops and bottoms of fractions. So I apologize that there's not enough space to sort of spread this out. I would encourage you to make more space as you're working. But you'll notice that the x minus 2's cancel, which leaves me with the x plus 2 times my 3. Here you'll notice that the x plus 2's cancel, which leaves me with the 4 times the x minus 2. And over here you'll recognize that the entire denominator cancels, leaving me with the original numerator that's on the right, 7x minus 2. Now what? Yeah, we'll distribute. I think somebody said it. Like so. So I have 3x plus 6 and 4x minus 8 to equal my 7x minus 2. 3x and 4x is 7x. 6 and negative 8 is... Yeah, at this point, we've run into something we've already seen before. It can happen with any kind of equation. It didn't have to be linear equations. We're getting into a problem here. Now, this question did not say classify these equations. So while it is an identity, that doesn't exactly answer the question it was asking. We still need to answer the question based on the fact that we know it's an identity. So what does an identity actually say happens? Say that really loud, Tiffany.
X is the element of the reals.
Okay, it has to be a real number. Any real number? Almost. Go back and look at the identity definition. There's one thing that we didn't have to deal with before, but we do now. In the domain. There are some numbers here that I cannot let x equal. What are they? Negative 2 and positive 2. You're exactly right. Negative 2 and positive 2. Why can I not let that happen, Elizabeth? Right, so if I chose x equals 2, or if I chose x equals negative 2, I'd have 0 in my denominator, yes? Okay, and that's a no-no. We're not going to divide by 0. That is an undefined operation. So on this one, my solution is I'll write it in words first. It's all x where x does not equal 2 and negative 2. I do have to write that down. It's not all x. There are a couple things that I cannot have. If you like the set builder notation that we talked about, you can do it like this with either the colon or you can do a line, and you say x does not equal 2 or negative 2 in either order. I think that it was, I'm still not remembering, Kylie. Sorry, Kylie, that asked me last time what would this look like in interval notation. Don't pay attention if you don't want to know, but it does look like this. That's how you actually write it out in interval notation. It doesn't matter to me in the slightest which one of these you like the best. Pick one. We'll talk about all of them later. But for what we're working with right now, probably either this one or this one's the one you're going to choose, and then you can just stop. You don't need to write multiple answers out. Any questions on this problem? All right. Let me make one more comment about this problem, then remind you of everything that's due on Tuesday. Let's say at this point you didn't recognize that it's actually working out the way that it is, and you decided to subtract the 7x from both sides. What would happen next? Not quite. Just the 7x. You'd get negative 2 equals negative 2. The one that we got before, when it was inconsistent, had two values that were actually constants, 0 and, what was it? Was it 2? 1? I don't even remember. But there were two constants that were not the same. So if you happen to not notice it right here, and you subtract the 7x, and then you notice, hey, it says negative 2 equals negative 2, you've still come to the same position where you're recognizing it's the same thing on both sides. It's an identity, and that's okay too. All right, so what's due on Tuesday? Well, you should finish P7 and you should finish 1.1. You also have a quiz on Tuesday. When you come to class Tuesday, I would beyond strongly encourage you to print out the notes, even if you're one of these people who are like, no, I really like taking my own notes. Tuesday, we're going to be talking in section 1.2 about word problems, and there's no way I'm giving you time to write my word problem down on my screen. So even if you like to take your own notes and you don't want to print mine normally, the notes that are out there for 1.2 are like Word document notes. They should be anyway. If they're not, let me know if there's a problem in Canvas. They should be like a Word document kind of a notes inside of a PDF, of course, but that actually allow you to have the word problems written down so that you don't have to write them on your paper as you go. Okay? So I will see you guys all on Tuesday.